Hello and welcome back to Calculus 1, section 4.5 on optimization. This is another section where you get to make money directly with Calc 1. We are interested in maximum profit, in minimum cost, in a whole bunch of different situations. So we want to also engineering. So we want to use the concept of min-max that we learned in the first section and now work this into the situations that you run into as you are designing things or running businesses or whatever. So we can start with the concept first. The idea of minimizing or maximizing should be clear. So, I mean, in terms of words, but let's see a generic math problem just to set up the process, and then we're going to do a real application. So let's say two numbers add to, let's say, 14. Find those numbers so that their product is maximum. We have two sentences. Sentence number one sets up that we have to add two numbers and get 14. How would you write that mathematically? Translating English into math. Perfect. X plus y equals 14. You can use A and B, you can use M and N, you can use X and Y, whatever you like. It's X plus Y equals 14, and that's the sentence the two numbers add to 14, right? So now, the next one says the product should be a max. How would you write that? Product equals a max. X times y equals max. There we go. So we converted two sentences. Now, the top one is called the constraint. And the bottom one is called objective. So we are trying to find the maximum product under constraint that the two numbers add to 14. So that's the red stuff is the math terminology, the math talk. The rest should be the common sense talk, right? So now we are supposed to solve this. And the way you solve these problems is you take the constraint and solve for one of the two variables. Let's say you want to get rid of y. So y is 14 minus x. And then you plug in. You will get x times 14 minus x equals a max, right? Because this part over here was your y. X times y is max. And now you have 14x minus x squared equals a max. Note that you only have one variable. Now we know how to look for max. We learned that, right? We take the first derivative. Huh. I'm allergic to someone in here. So that's going to be 14 minus 2x equals, now maximum is some number. We don't know what it is, but we know it's a number.
0.
So derivative of that is 0. Derivative of a number is 0. Remember how in the first one we memorized? Well, we didn't memorize. We argued that mean and max happen when you have horizontal tangency and the slope of horizontal line is always 0. So we said set equal to 0. Over here, you don't even have to set it to 0. Derivative of max or derivative of min is 0 because min and max are some numbers. And from here, we quickly deduce that x is equal to 7. And now, y is equal to 14 minus 7, also 7. So the answer is x equals y equals 7. Now let's say you would like to challenge this. Well, you can run through calculations with integers to see if this works. So 0 plus 14 is 14. 0 times 14 is 0. 1 plus 13 is 14. 1 times 13 is 13. Okay, product is bigger. 2 plus 12 is 14. 2 times 12 is 24. Okay, it's going up. 3 plus 11 is 14. 3 times 11 is 33. So you see how it slowly is creeping up. And we are expecting for the maximum product obviously to be 49 as we go. So 5 plus 9 is also 14. 5 times 9 is 45. 6 plus 8 is 14. 6 times 8 is 48. And now, if both numbers are 7, which adds to 14, you get 7 times 7 equals 49. As soon as you go 8 plus 6, right, to continue this pattern, 8 times 6, it's going to go and start dropping again, all the way down to 0. So just by running this calculation, because these numbers were small, we saw that we went all the way up in our product to 49, and then the product started dropping off. And if you continue the pattern, 9, 10, 11, and so on, it will drop down to 0, and it will reveal that obviously 7 and 7 would give us the largest product. So this is the idea. You get some word problem, and in that word problem you will have a couple of sentences that you need to convert. In Calculus 1, you are only dealing with two variables, x and a y. You can put those variables to be any other letters. And you are looking for min or a max. Calc 3, you can have as many variables as you want. We'll deal with 3 or 4 in Calc 3 using something called Lagrange multipliers. Yes?
So you do substitution and then you find the derivative of the substitution?
That's it. Plug the constraint into objective to eliminate one of the variables. And once you eliminate one of the variables in objective function, you take the derivative of the objective function because it will have only one variable. And that's the variable, that's the objective function is the one that you want to find the max. If you're trying to maximize a function, you will find x at which it has a maximum. That's why you are differentiating that function.
So whenever it's a max, you want to find x? Like do you always set it equal to y?
No, you can do whatever is convenient, okay. Right? Whatever is convenient. We'll see that. So the most famous problems are farmer problems. The farmer problem. How about that? Farmer has 200 yards of fence and he wants to fence off a rectangular area of maximum size. What are the dimensions of the rectangular plot? So farmer has land. Farmer has land. And what is happening? He wants to put a fence around a rectangular plot, or to put something in there, whether it's animals or whatever. So we know that he is going to fence off a rectangular area xy, a, b, whatever, length, l, length and the width, or width and the height, or whatever. You can use any letters. What is the sorry, I said 2,000 yard of fence, and I put 200. 2,000 yards of fence. 2,000 yards of fence. Good. So farmer has 2,000 yard of fence, and he wants to fence off a rectangular area of maximum size. What are the dimensions of the rectangular plot? Right, so, or rectangular area, plot, whatever. How about rectangle? I can change area into plot, whatever. So, we have rectangular geometry, right? What would be my constraint looking at this problem? What is your constraint? You are a farmer.
2,000 yards.
2,000 yards. Where does that go?
It has to be 2x plus 2y.
Excellent. It's a perimeter. Perfect. So the fence goes on the perimeter of the plot. Therefore, 2x plus 2y equals 2,000 is your constraint. Right? You don't have more than 2,000. So that's your constraint. Now, what is your goal? What is your objective?
2x plus 2y. Well, no, it's supposed to be 2,000.
Well, you want a maximum area.
Yeah, I want the maximum area.
So it's going to be x times y.
Beautiful. Same like last time. So now, and that's, so this is our constraint, this is our objective. So your objective is always something is getting minimized, maximized. Now we're trying to maximize area, so again, x times y. We can divide the top equation by 2 to reduce numbers. So we are going to have x plus y equals 1,000. And from there, y is equal to 1,000 minus x. Plug in into objective. We get x 1,000 x equals max. And then you have 1,000x minus x squared is equal to a max. And now, as you can see, your objective equation has only one variable, variable x. This is where you hit this with the derivative in respect to whatever variable is present, and you will get 1,000 minus 2x equal to 0. From where x is 500. Well, y is 1,000 minus x, which is 1,000 minus 500. So we get x is equal to y equals to 500 yard. And we see again, we are getting, in this case, right, we're getting, so that's our answer. Good.
I have a question.
Yes.
I remember learning this, I think, in pre-calc or something, but it was like a different way to get to 500. It's like you would have like 2x plus 2y equals 2,000, but then you plug something into one of them, so it'd be like 2 parentheses something.
You were looking for the vertex, but all of your equations were quadratics. So yeah.
But it was just like the farmer plotting where it's like someone's trying to fence off something. That was the vertex.
Yes, because you have the quadratic, right? This is a quadratic.
Yeah.
So because it's a quadratic, it will have a vertex, and vertex happens where the maximum point is. So you can find x coordinate of the vertex for a quadratic, but that holds only for that one case, right? It all goes, right? If you put in trig, if you put in e, like the whole thing you learned in pre-calc becomes useless, right? So in this case here, it will work. All right. Well, here's more of a farmer. Now we have a river.
It's not connected. Oh, there it goes.
Now I'll put some salmon in it. My salmon looks like carrots, but it's salmon. And you know how I know? Because if it was a carrot, it will have a green stuff at the end. Now these ones clearly don't have green stuff, so it's not carrots, it's salmon. So we have a river, and now we're going to put our rectangular plot right there with, again, x and a y. We still have 2,000 yard of fence. What are the dimensions now? Does this change anything?
Yeah.
Yes, it does, right? Because we do not have fence against the river.
So it's x plus 2y equals...
Excellent. So that's exactly what's changed. X plus 2y equals 2,000, and we still have xy equals max. Now, in this particular problem, right, if you solve for y, you run into trouble called fractions, right? So in this problem, it's easier to solve for x. So we're going to take our constraint and say x equals 2,000 minus 2y, and then we're going to plug in into our objective function to get 2,000 minus 2y times y equals a max, and now you'll have 2,000y minus 2y squared equals a max, and as you can see, you have objective function with only one variable. So you can solve for any of the variables. It's just, question is which one is more convenient. Now we're going to differentiate in respect to y, because that's the variable in the problem. And we get 2,000 minus 4y equal to 0, from where y is 500. Now, before you jump screaming, it's the same, look at x. X equals 2,000 minus 2y, which is 1,000 yard now. So this time, dimensions are 1,000 by 500 yard. And that should make sense because you are not boxing off all four sides, so you have more fence for other sides, and by doubling x actually from the last time, right? All of the fence that was on one x moves to the other x, and now you have maximum area. So what these problems guarantee, these dimensions, they guarantee the largest area. If you fence it off in any other way to use all 2,000 yards of fence, you are going to get smaller area than if you do 1,000 by 500 if you are adjacent to the river, right? Let's say now that the farmer wants to separate whatever, animals, plants, whatever it is, into bins. So he puts this, he also uses fence for the inside. Now you can have this against the river, right? So there are a lot of different configurations you can have. So now we're going to call all of this x, this one y. We still have 2,000 yards of fence to play with. What are the dimensions now? Does this change anything that we introduced two divisions in the middle?
Yes, before y.
It's going to be 4y. So 2x plus 4y equals 2,000, and again xy equals mx. And if you divide this one by 2, you get x plus 2y equals to 1,000. X is 1,000 minus 2y. And now we plug in. So we have 1,000 minus 2y times y equals a max. 1,000y minus 2y squared equals a max. And we differentiate in respect to y. That's 1,000 minus 4y equals 0. And here's your y as 250 yard. X is 1,000 minus 2 times 250, which is 500 yard. So now the dimensions are 500 by 250 yard. We can think of all different kinds of divisions and shapes. I'm just going to leave one configuration for you to try at home. Try, let's say, farmer goes like that. So this is going to be dimension y over 2. This is x over 2. You still have your y, you still have your full x. Anywhere where you have the black line, it's a fence. So it's going to have more features here. Obviously introduce fractions, and you just plow through the same calculation. You still have 2,000 yard of fence, and you're still looking for the dimensions in terms of x by y. So try it at home as you practice this. What I would like to do is see some other problems that are cool to consider. let's go with this is a pool. So there is a pool, in ground pool, that is, let's say, 100 feet by 60 feet, doesn't matter. 100 feet by 60 feet, whatever. Now, we want a concrete walkway around it. So this is the pool, and this over here is concrete. We want it so that this over here is at least 10 feet and we want this hold on. No, this is, I'm doing this, we're looking for this. So this is 10 feet, and this, let's say you want this to be 8 feet, at least. You have your dimensions inside, X and a Y, and you want the, you know that the pool has the area, so that's important, of, let's go with 5,000 feet squared. There we go. So, area of the pool is 5,000 feet squared. What dimensions we should build the pool so that the amount of concrete is the smallest possible. So we're looking for X and a Y so that we use the smallest amount possible of smallest amount of concrete, and then there's a word possible somewhere in there.
You make them into fractions.
Well, we'll see where the math takes us, but we know that the pool is going to have 8 feet of concrete from one end, 10 feet of concrete from the other end, but then the dimensions of the pool will govern the lengths of X and a Y, which case we can end up having lengthwise huge area of concrete, right? You are already willing to pay for the pool of 5,000 square feet. Do you really want to add additional huge cost for the concrete? You can make the concrete even smaller, 6 and 8, let's say, but put the chairs and have the chairs are 6 feet at least, maybe even 7 feet. So you want to at least a little bit to walk around. All right, so what is my constraint over here?
It's got to have the 5,000 square feet in there.
Good. So what's the constraint? What should I write mathematically? Excellent. X times y is equal to 5,000. Because the area of the pool is 5,000 and I have unknown sides for that pool. So X times y is 5,000. Now, my objective is to minimize the area, the overall area, right? So, what's my objective function?
You're going to have to include like your 8 foot and 10 foot in there, so it's going to be 20 and 16 respectively.
Excellent. What do I do with 20 and 16?
So you're going to want to add 20 to X and 16 to Y.
Excellent. X plus 20 feet is the length of the concrete this way. This is X plus 20 feet because the side of the pool is X and I have 10 feet added on each side. That needs to be multiplied by Y plus 16 and we're looking for that to be the minimum. Because again, you want to minimize the area of the whole thing. Now the pool is always 5,000 feet square. So clearly by minimizing the surrounding area and pool being fixed at 5,000, you are minimizing actually just the concrete. So now we solve for either X or Y. We can solve for Y, 5,000 over X, plug in, and just grind through calculation. So X plus 20 times 5,000 over X plus 16 equals a minimum. Now we are going to multiply algebra, right? Foil this because we don't want to do the product rule if we don't have to, right? So 5,000 times X is just going to be 5,000 plus 16X plus 5,000 times 2 is 10,000 and a 0. So that's 100,000 over X plus 320 equals to minimum. So 5,000 times 2 times 10. 5,000 times 2 is 10,000 times 10 is 100,000. And 16 times 2 is 32 and a 0, 320. That number is not important because now when we hit it with derivative, it's going to die anyway. But take the derivative in respect to X. So 5,000 goes to 0, 320 goes to 0. The numbers that we are talking about is 16 minus 100,000 over X squared equals to 0. So 5,000, derivative of that is 0. 320, derivative of that is 0. Derivative of 16x is just 16. The derivative of 1 over x is negative 1 over x squared times 100,000. So we have 100,000 over x squared is equal to 16. 16x squared is equal to 100,000. X squared is equal to 100,000 divided by 16. So is now going to we take the calculator for applied problems, divide by 16, and then we take the square root of that value, to get 79.05 blah blah blah. So x equals, now you will get the negative number as well, but we only know that the lengths are always positive, so whatever. So 79 feet for x. Now you do have equation for y. Y is equal to 5,000 divided by 79. So 5,000 divided by 79. Obviously not, right? Let's see if this. So the projector is
checking them on old 200 feet squared.
no. So that's the way you do this problem. It will restart. When it restarts, we will do the next problem. I want to still talk a little bit about this problem. It doesn't have to be, in notes. This is just a talk. I had a problem that had the walkway around a pool. What we can do is we can stand this problem up like that and put this and say that this over here is 1.5 inches and this over here is 1 inch and this over here is 1 inch and this over here is 1.5 inches, and it becomes the same problem for margins of the book, right? Do you think that they compute these things? Hell yeah. Why do they compute these things?
Save paper.
To save on paper. You know how you can't find two books that are the same size? You put them on the bookshelf and they're all over the place. It's the content worked out in mathematical equation. Printing books is insanely expensive. Insanely expensive. You know that your textbooks are $300. For calculus, $300 divided by 3 courses is $100 per course, right? And then you have, if you're buying the textbook, to have it for all time. So when you take a look at that, and then you also consider there are 1,500 pages inside, divide 300 by 15, right? 100, you will see what is the cost per page, right? So all of those things, if you read the book, it actually works out to be extremely cheap. But it's extremely expensive to print these things when you consider not just the design and the author fees and all of these kind of things. You also have to worry about paper, the weight of the book, the transport on trucks and everything else to go everywhere around, which is why online is killing it, right? They have no warehouse costs. They have no printing costs, distribution costs, right? And you still sell the book over the website, so both have websites. So technically the cost of ebooks is negligible in comparison to the printed book that has to be, right, run through a machine to be printed, to be assembled and glued with a hard cover or soft cover, whatever, then packaged into boxes, put on trucks, distributed. Someone had to load it, someone has to unload it, someone has to put it in storage. Someone has to display it on the shelf and then eventually sell it. Everyone has to be paid along the way, which is why the books are so expensive. But the way to minimize the cost, at least a little bit, is to compute this thing. And when you compute this thing, which is the same problem like a pool, you know what the surface area of the text that you have inside, you know that surface area. And then you know what margins you want. You want an inch on each side, inch and a half, or whatever margins are, and you run the exactly same calculation. And when you run this calculation, it comes up with this.
So, you know the font size, right?
Mm-hmm.
And you know the total word count. So like there are have to work out how many pages beforehand, right? And then
Well, the number of pages will also be determined through, once you have the surface area of how much you can stuff on one, right? So they know those things. The issue is to minimize the size of the paper. Remember, you have 1,500 pages. It's 750 papers, right? Two-sided. If you have 1,500 pages, that's 750 papers, pieces of paper. And having those papers smaller times 750 pages times the amount of books you are printing, it adds up to reduce the cost. Yes?
I had a question before we forget, because I know from last time, did we have class on the
No. It was confirmed by the HR that the college is open but classes are canceled, which is why it's so confusing. Yes. So on Wednesday you can actually come to school and roam around, but classes are canceled. On Thursday, college is closed and no classes, so buildings are locked. So that's the difference between Wednesday and Thursday, and that's why they have two different lines there. I said, all right, fine. You guys definitely win on this one. I'm not even going to question it.
Why would you open?
That,
Well, do they have in-service days here like they do?
No.
I don't know why.
No one knows that. I don't think that even NSA or FBI would know that. That information is confined within some brain somewhere in administration, and dragging that information. Yeah, very interesting experience. Anyway, the last problem is going to be, all of these problems are the same. Write two equations, constraint, you're done, right? Plug one into another one, done. This problem is going to be the problem where you are contracted by the almighty oil company, right? To do some calculations, and what they want to know is, over here we have a shore and sea on this side. There is an oil rig right there, which is drilling the oil, and it's very close to the shore, let's say 5 miles off the shore. You are not going to run a tanker, right, huge ship, back and forth between the oil rig that it's so close to the shore. You're going to build a pipeline and then get the raw, right, oil. But the trick is that there is oil here, and there's oil here, and there's oil here. So refinery for oil is right there. The job of refinery is to take the raw oil, right, and turn it into gasoline and diesel and plastic and rubber, right? That's why we are digging for oil. So now, what we have are the two different prices to make the pipeline, and I have to make those up, okay? So I'm going to say that 1 mile under water equals $500,000 in cost to set up the pipe. Now, if you think that's too much, I will tell you that to run one tower to another tower with a set of wires in between, so you're not including the second tower, just one tower with a set of wires is $100,000. Okay, one tower with one set of wires on one side, and then when you drive home, you look through the window, you see 10 of those, that's $1 million right there, right? So to run 1 mile, I can just, put a price of 50. To run 1 mile pipe on ground, let's call it 250. Now, what I'm going to say is that this is 5 miles, and over here, 10 miles. And then I'm going to have the blue path this way. So I have a black path that uses the minimum amount of water, so you decrease the cost as much as possible using $500,000 per mile. But then you have the maximum length on ground. As you can see, the blue one has nothing on the ground because that's the shortest possible distance between the oil rig and refinery, right? So we can run these two costs and see what they are. So black cost, 5 million. So 5 million to go black path. Shortest amount through the water because that's insanely expensive. Now, blue cost. Well, I have to figure out the mileage first. So the distance is going to be the square root of 5 squared plus 10 squared. And that's going to be root of 125, which is 11.2 miles. So the cost would be 11.2 miles times $500,000 to give me 5.6 million. So these are the costs that even administrators can compute, okay? You are contracted to see if you can make this better. And your idea is obviously the red path. And the red path is, how much do I have to go this way? And how much do I have to go that way in order to come up with the minimum cost? And this one over here we can call, since we call this one D, let's call this one L, length. So that's it. Now, what's the red cost? The red cost is going to be 250,000 times X plus 500,000 times L. That's your cost. And you want to make that into a minimum cost, which gives you your objective equation. All you need to do is to take a look at any combination here that would link X to L. And that is hidden in this triangle here.
Yeah, you have the distance and your hypotenuse.
This distance here is 10 minus X. So you have a Pythagorean theorem. L is equal to the square root of 5 squared plus 10 minus X squared. So try to work this one out at home, right? Because you will now plug this in there. I know we're over time, so I don't want to keep you. You will plug that for L, and then you will work out this algebra here so it's easier to take the derivative. And you will see that you will save considerable amount of money to this company, which is why it's nothing for them to give you $30,000, $40,000 for this calculation. And if you know Calc1, you can do this in 15 minutes. That's a good deal. 30K for 15-minute calculation, right? Right. And they don't want to employ anyone. It's a contracting job. They don't want to employ anyone for that, because why would you be paying someone, 100K a year all the time for 15-minute calculation that they can just contract you for 30K and be done with you, right? But then you go to the next one, you go to the next one, you go to the next one, right? This is always something to do. So think about that, and I will see you guys Monday, and we'll finish up chapter 4.